It's okay.
Okay, welcome everybody to our today meeting, to our lecture actually. Unfortunately, it happens in this situation when we can meet face to face in our big auditorium. Okay. But everybody, I like that you can come here to this virtual meeting. Unfortunately, it happens in this so that we can meet face to face. Discuss maybe together. So I'm expecting some questions from you. We'll discuss the topic which combines mathematics, geometry, trigonometry, and physics of gravity. And it relates indeed various aspects of our understanding how our world is constructed. So my name is Evgeny Kolomeitsev. I'm working at Univerzity Mateja Bela, at Department of Physics in Banskej Bystrici. So personally, I'm in my research connected with the physics of neutron stars, heavy ion collisions, and everything what happens in dense nuclear matter. So the title of today's lecture is Measurement of the World from Gauss to LIGO, and how we can probe the fabric of the universe, the substance from which our universe is made from. And we start with a very simple question: how do we measure distances? Once upon a time, there were two kingdoms, and accidentally they learned about each other, and one of the king wanted to know how far away his neighbor is, whatever purpose he wanted, for trading or for war, and how he can learn how far the neighboring king is. Take the best of his guy, who runs as fast as he can, and send him. Please tell me how fast you can go to this my neighbor and come back. And the runner or the traveler makes his way, little stops, going around, and then comes back. And the king sends him again. Say, try to do faster. Faster and faster, send him many, many times, measuring the time when the travel needs to go to the neighboring kingdom. And pick up the shortest time and say, okay, now you were not lazy, you were moving along the straight line, and this is the shortest time. And the same operation he did with all other places where he wants to know how far they are, for example, gold mines. So for the king, distance is the shortest time in which the runner can move from one place to another place. The only one problem, or the wishes of the king, to have the really good runner who is not lazy, doesn't make turnarounds, not sleep on the way, and runs as fast as possible. And this type of runner, good runner, existed in history and used in Africa, for example. It was camel. And here on this map we can see the camel caravan routes passing through Sahara, and indeed going in these very dramatic, dramatic conditions when extremely hot and cold in the night. The traveler wanted to make the passes as short as possible, and you see they really travel almost along straight line, unless there was some really unavoidable mountains or something like this. Another property of the runner, of this camel, which served as a runner, was that in one day camels makes approximately exactly the same amount of kilometers. So one can measure distances in camel days, and it was used in history. Okay, so if we compare several statements and want to go to physics, and it was used in history. Okay, so if we compare the units, several statements, and so we want to introduce units, because units serve to quantify comparative statements. Like, for example, Bratislava is bigger than Banskej Bystrica, but Banskej Bystrica is closer to Zvolen. So this is absolutely true statement, but it's philosophical in some sense. So it's just, it's not quantitative enough. So in mathematics, when we do, say, larger or smaller, we deal with dimensionless quantities, just the numbers. So when I say that my height is 5 and yours is 3, doesn't imply that I am taller, although 5 is bigger than 3. Of course, I can say each measurable quantity can be measured in its own units. For example, I measure my height in my units. And so, this above statement, I can say my height is exactly 5/1/5 of my height. And your height is exactly 3/1/3 of yours. But again, still we cannot conclude who is taller from us. So we have to insist on one particular unit. So I have to impose that everyone uses. So we have to insist on one particular unit. So I have to impose that everyone uses. Okay. So we have to insist on one. Okay, sorry, it was an echo, probably. Now it's eliminated. So the idea is that someone of us, me or you, has to say, we want to measure each other in my units, my own. Of course, it can be done only by the king. So indeed, that was done in England. Henry I of England introduced yard as a distance between the tip of his nose and the end of his thumb and the straight end. King is a king, and so this yard, this measure, was put on the wall, and everyone in the country could come here and compare and make the measure of the yard and use it. Of course, when the Henry I will be replaced by Henry II of England, the yard changed a little bit, but fortunately it's not so much, because on average this distance, the sizes of human body are on average the same for everyone. So these so-called person-oriented measures of length were used through all the history of mankind. For example, starting from Egypt, they used the standard measures: cubit, hand, foot, and pace. And here, for example, the photographs of the real, very, very old type of cubit standard, which measured of course, from the pharaoh hand. And if you can see, so that the cubit also was divided in some subdivisions. It's like centimeters or centicubits. Actually, it was not 10 division, but in the 5 division, in the 6 divisions, if you can see. So because it was very important measurement standard, it was made out of granite. Also in Russia, the standard usage was the following sizes, like this spread or this diagonal spread, and also the same diagonal goes to yard and to hand and so on. So of course, these human-related measures must be forced by someone, some important persons like king or noble person. Everything changed by the Great French Revolution, 1790, when of course égalité, fraternité, and liberté was proclaimed, and so it must be used not king measures to measure distances. So astronomers said that we can use something which is common for the whole mankind, and this is the size of the Earth. That time it was approximately measured quite well, so they said, let us use as a meter 10 millionth part of the Earth meridian, or the half meridian, going from North Pole to equator and passing through the Paris, because it was an observatory that it was possible to make measurements. So it was proclaimed as the meter, and during Napoleonic War, which spread over the whole Europe, this idea about this measurement related not to the human body or to the body of the special human in the country, but to something more basic for everyone, was spread over the whole Europe. So the meter convention, which relates many measures exactly to the meter, was take place on May 20th, 1875 in Paris. And of course, immediately the meter was put outside on the wall. So here is a meter, everybody come and compare his measurement, or take the measure of the meter with himself. Now, afterward, there was made, of course, a talon of the meter, which has this famous form. Actually, this is so-called treska section, named after the engineer Treska, who calculated this particular form is the most resistance to the bending. It made out of platinum iridium alloy, because it changed to the smallest degree its size when you heat or the cool this metal. And there was 2 marks here, and this marks was used. The distance between these 2 marks was set is exactly 1 meter. So it was one primary or a 0 etalon, and it was made 31 the first grade etalons, which is spread or distributed among different countries. So this measure related to this piece of metal hidden somewhere in Paris was used till October 14, 1960. Okay, coming back to the measurement of distance, we come to the new kingdom somewhere between India and China. Here is sitting the king, and want to know the distances to this place, which is not far away actually from the capital. And of course he can send the runner, and after many attempts he would know how many days or the hours this runner will take to reach this place. Suddenly he learned that there is a very rich country, very interesting country to the north from the capital. He want to know how far away is to the nearest city. Trying to send runner, and runner never comes back and said, or coming back and said, I cannot reach this country. Or they try to go a different direction, it never comes back because it's too far away. And it's not wondering, because this is the kingdom of Kathmandu, and here is in Nepal, and there is the mountain Everest in between. So the high difference here on this way is 800 meters. So it's really, for the runner or whatever it is, it's very difficult to cross it in the direct way. So one neat method how to being able to measure distance in all possible directions, nevertheless to calculate the distance between these 2 points, which can be directly connected. So this method was invented, and it's based on very famous for all of us theorem of Pythagoras of Samos, who said that if we have right angle triangle with a side A, B, C, this is hypotenuse, prepona, and 2 otviasi, cathets, B and A, then there is this relation among them. And there was already found the special numbers, or the integer numbers, which satisfy this relation. We know it from school, this 3, 4, 5, this is the favorite numbers which appears in the textbooks on Pythagoras theorems and the problems, or the multiples of them, 6, 10, 8, and so on. The other triple is, for example, 12, 13, 5, and so on. There are infinitely many of them. And it turns out, although this theorem carries the name of Pythagoras, it was known many, many years, or in the centuries, or in 1,000 years before him. Already in ancient Egypt, the rope with 12 equally distant knots was used to build a perfect angle. There are special people, so-called rope stretchers, who hold this rope in this way, so the distance 3, 4, and 5, and if you pull them, then this angle will be exact 90 degrees. And in the construction, in the construction of in ancient Egypt, you can find the ideal right angles. So they know how to do this. So they know these three magic numbers. What we know from this about the Egypt mathematics, we know from, for example, from so-called ringed mathematical papyrus, which is dated 1550 years before Christ. And the Egyptians liked these magic numbers, so they identified with the gods and give special name to the sides. These sides with three intervals, it was called Ausar, or in westernized translation Osiris, that makes origin. The side with four gives was named Auset or Isis, the meaning recipients, from origin to recipients, and it result 3 plus 4 was not 7, but result in 5. Heru or Horus, it makes perfect result. Even before or in the same time as Egypt, and maybe even earlier in ancient Babylon, the people knew about these Pythagorean triples, 3, 4, 5, 5, 12, 13, and so on. For example, this Babylonian clay tablet, which is his own name is Plimpton 322, by the name of the guy who first bought it and described it. You can find here encrypted several of these Pythagorean triples. So this particular Plimpton 322 clay tablet is dated back to the 1800 before Christ. It's quite old. So after it, from Pythagoras, it turns out that these quantities can be made independent on the sizes of the triangle. So I just divide left and right side by c squared by the length side, and we'll get this relation and get some universal number 1. And then these quantities, which by definition will be smaller than 1, at the end turns out to be named as a sinus and cosinuses. So trigonometry is born from this Pythagorean theorem. 16th century, René Descartes revolutionized our geometry. He said that we can, instead of dealing with the points, distances, and intervals, we can deal with numbers, introduce algebraization of geometry, saying that if we introduce some axes, the coordinates, then each point can be described by two numbers on the plane, and so we can do all the geometry basically operating with these numbers, saying, for example, the distance between 2 points, A with coordinate AX and AY, and B with coordinate BX and BY, will be calculated like this. And this is again another form of the Pythagorean theorem. Discovery is that again we can deal with numbers. And here appears this combination. Now finally, how to use this theorem to measure distances. That is invention, again you see 17th century, 1615 by Willibord Snell van Rooyen, in Latinized name Snellius, invented the idea of triangulation. If I have 2 points, A and B, and I know exactly the distance between these 2 points, and then I want to measure distance to the point C from A and B, what I have to know? I have to measure just these 2 angles. And exactly this operation is symbolized here. So here is the basis, hypotenuse, catetus, and we can measure the distance from this point to this, and from this point to that. The relation is very simple, and again it's written through the sinuses and cosinuses. So sinus and cosines again rooted in the Pythagorean theorem. Direct physical or practical application of this discovery was that Snellius worked out the distance between 2 Dutch towns, Alkmaar and Berge, Berge op Zoom, this is the name, Zoom is a river, and using the network of 33 triangles. So quite a work. But why he used this? Because these two towns, Alkmaar and Berg op Zoom, lay on the same meridian, and looking at the sun, you can figure out that the parallel differs by exactly 1 degree. So knowing exact distance in the meters, or whatever units, he was able to figure out the size of the Earth in the meters or in the particular units that he wanted. So the well-known statement, or the following of the Pythagorean theorem, is the sum of the angles in triangles is exactly 180 degrees. This statement, the proof is just shown here. It's very simple. If you look at this construction, it follows from the parallel postulate, or Euclid 5 postulate, which tell us that two parallel lines, to construct them, in other words, they have to cross some third line exactly at the right angles, two angles 90 degrees. Then they will never cross, because unless the sum of interior angles alpha and beta here is less than 100 degrees, then two straight lines will cross. If they exactly equal 180 degrees, it will never cross this. So taking this postulate, one can make this construction, drawing this line x parallel to BC, and you see that indeed the sum of this angle is exactly open angle of 180 degrees. So again, from and the right angle we can define through Pythagorean theorem 3, 4, 5 using Egyptian method. So again, this is going back to these roots. So this gentleman, Johann Carl Friedrich Gauss, who was portrait was on this well-known piece of paper, quite valuable at that time. What he did, he applied this method of triangulation invented by Snellius to make exact geometric survey of Kingdom Hanover, and connected this to the geodesic survey of Denmark and Holland, which was made at the same time. By this, he invented the instrument heliotrope, which on the other side of this banknote, and this is instrument which uses the sun. You see there are several mirrors system to signal to some distant point. By this, you can measure angles very exactly. So, but Gauss was the first who was thinking actually these relations between the angles in the triangles, that the sum is 180 degrees, has something to do with that the Earth is, for us, looks like flat. But actually the Earth is not flat. What happens then? Then if we do the measurement of very big triangle, as Gauss was thinking, then maybe this relation between sum of the angles of triangle is not equal to the 180 degrees, not valid anymore. And here is example. So this is the sphere, we are on the equator. On equator, very locally, we can make the right angles. 3, 4, 5 Egyptian method. So starting from equator, we can send two lines strictly perpendicular to this equator line, to line AB. According to the Euclid 5, these two lines should never meet. And we see that actually if we draw this line on the sphere, again we can check on every longitude. So in every line here, we can again use the method 3, 4, 5 Egyptian. We can see that this will be exactly right angle to any line parallel to the equator. So they will be perpendicular to this line, to any longitude. But nevertheless, if we prolong them, they will meet at the North Pole. So now we get a triangle. We have straight line, which we draw as the straight lines, A, B, C, but in this triangle, we see this is 90 degrees plus 90 degrees already 180, plus this angle, which can be even 90 degrees. So the sum will be for this triangle 270. But this valid only for big triangles, which feels that the surface is not flat. If we make very small triangles, like now study books, then we don't see this difference. Everything looks flat for us. So for this situation, the sum of the angles in triangle will be larger than 180 degrees. We can imagine another kind of surface and another construction of the triangles. So the number of the sum of the angles in such triangle again will be now smaller than 180 degrees. But again, if we make the triangle very, very small, we don't see the curvature, that this is bending surfaces. So what is the difference between this situation and that situation? Let's write the simple formula. For the sphere, we know how it looks like. We call this positive curvature. So if this is coordinate of the point on the sphere, to be on the sphere, the sum of the squares must be equal to the radius. So in this situation, let me put 1. What about this type of surfaces? Let me give you just one example. These surfaces are called surfaces with negative curvature, and this is so-called hyperboloid. And the formula looks very, very similar to that one. The only difference in this minus. Please keep this in mind, because in some minutes you will see that this changing in the minus, plus into minus, has something to do with our physical reality. Okay, there are surfaces with so-called positive curvature and negative curvature. They can differ in simple example just in the size, in the sign in front of one of the components. So what happens if we have not such a simple surfaces like this sphere or this hyperbolic, if this is really strange surface? Can we quantify it locally in small distances? Yes, that was invented with using the method of parallel transport. So idea is very simple. So you stay in front of your house and put straight your hand horizontally, pointing in some direction. And then you can try to move somehow left, right, or even jump if you want, but keeping your hand pointing in exactly the same direction. You can easily do this in front of the house. So here, if you move. But now if you take a long journey and with your hand straight ahead, you go, for example, to the south, to equator. Then, if here on the North Pole your hand was pointing like this, then on the equator, to be parallel to this line, it also must point like this. Yes, so then this would be very strange for you, because you said, why going to the equator I should suddenly start to point my hand upper and upper, right to the sky? Because if I go in another direction, for example, direction orthogonal to direction of my hand, I have to do nothing. And you can say, no, I don't want to do this, because this I don't know how to do. How? What I will do another rule. So just locally I will always pointing my hand parallel to the surface. And then see what happens. Yes, you can happily move down to the equator. And then here your point will look in this way. But you can take another way. You can point. Go first perpendicular to the direction of your hand, to equator, and go along this direction of your hand. And you end up in the same point, but you see your hands pointing in absolutely different direction. So this is the measure, actually, of the curvature along the passes which you take. And this measure can be made local. For example, you move here a little bit step by step, and you can calculate how exactly you have to adjust your hand to go it up and down to perform real parallel transport. And this measure is called local characteristic of the curvature. So using this little measure, one can define what is called geodesics. So-called straight lines, or the shortest distances between 2 points on the curved surfaces. So the method which we discussed before, which was first thought about about which the Gauss was taught, can be made locally for arbitrary surfaces. And these measures, exactly, and then we will see, this is what the people try to measure in experiments with little differences. So if you think that everything what I said is nothing to do with reality, this is how the flight of the airplane between London and Los Angeles looks like if you put the Earth flat. It doesn't go on a straight line. This, what is shown here, is exactly geodesic on the sphere. Okay, now we come back to physics and how it is everything related to Pythagorean theory. So the big step in the physics was done by Galileo Galilei, who first of all said that you don't have to look straightly at the result of some experiments, or you always have to try to figure out what is essential in the experiment and then try to cast in mathematical form. He was the first who said that physics is based or must be set in the language of mathematics. So the physical law is not just the words, but it must be relation between physical quantity written in mathematical terms. So this is one his contribution. Another is his invention or discovery of principle of relativity. So this is some text which maybe you can read after because it's nice words from dialogue concerning of two-G world system, in which he advocates the Copernicus system of the world, 1632. And the idea is that if you sit inside, go down in the ship, inside the ship, without with all window closed, and you can go here with the friends, have a nice dinner or something, and make little experiments. For example, you have some fishes in the bowl, or some water dropping from the ceiling, and some butterflies flying. Then sitting only inside, without looking outside, and looking on all these phenomena which happens in the closed room, you can never decide if this boat is staying or swimming or moving somehow. So this is the principle on which the whole physics is based. Now, in all physical law must have exactly the same writing independently in which system we are. And this lead to so-called Newtonian world. Newtonian law were the famous Newton law, which we know from school. Law number 1, law number 2, law number 3 are valid. And all this law, whatever you write in Newtonian physics, is invariant under so-called Galilean transformation. What it means? That if I have, for example, something happening to different points, and the forces or the phenomena depending on different points, then in physical quantity can enter only the distance between 2 points. Now, if this system, I look from the train passing by, or from even sitting on the bicycle, I move with some fixed velocity, then of course coordinates of these 2 points will change. To each of them will be added terms my velocity times time, to these 3 numbers and to these 3 numbers. But as Descartes and Pythagoras, they said that distance between 2 points can be calculated like this. And all coordinate. So first of all, there is a difference. So here all these additional terms like relative motion of myself with respect to this system times time will cancel exactly. And then there is the symmetry here. You see, again, there are all the pluses here. Of course, in the big physics, there is additional transformation like rotations, but it's for a moment not important. Here, to work, is the one important thing happens, that the time which runs on my clock and the time which occurs in these 2 points is exactly the same time. So-called global Newtonian time, one time for the whole universe. And all events happens in this common time. which goes from minus infinity to plus infinity, from past to the future. So everybody was happy with this. All Newton law, all mechanics, even thermodynamics could be understood in this before the people start to understand electromagnetism. So Maxwell wrote his equation, described in 4 differential equations. I will not write them down. The all phenomena of the electromagnetism were described. And Einstein was the first who looked closely in these equations and actually said, I will a little bit extend this Galilean transformation, and said that the laws of electromagnetism must be also independent on the coordinate system and how I move with respect to this phenomena, or the phenomena of electromagnetism. But the equation, Maxwell equation of electromagnetism, are not invariant under this Galilean transformation which we studied before. If I apply this one, they will change their form. Because we know that electric charge, if we take one electron at rest, it has only electric field, no magnetic. And if electron moves with respect to me, then there is a magnetic forces. But otherwise, if electron moves with respect to me, but I'm moving now together with electron, suddenly the magnetic force must disappear, but electric force must appear. So there is an internal relation between the coordinate, or how fast the electron changes its coordinate space, and changing in time. So the discovery what was made, that measurement of distances and time intervals, they are not independent. And then appears that because the laws of electromagnetism, Maxwell equation, at the end was found the transformation under which these equations are invariant. And from Maxwell equations one get also equation for electromagnetic wave, for the light. And there is no free, in vacuum there is no parameters, there is only free parameters. There is only one number which enters there, so-called speed of light. And because this equation for the electromagnetic wave must be valid in any system, irrespective of how fast it moves, we can conclude that the electromagnetic wave must propagate with the same speed for all observables. It doesn't matter how fast or slowly I move with respect to the light. If with respect to me, to any observer, light will always move with the same speed of light. This is 300,000 kilometers per second. Enormous speed. It's almost infinite. So because now there is relation between some time intervals and space interval, we must be very careful how we define time, for example. And if we want to measure time intervals, or the distances, because to measure distances we need time intervals and vice versa. So we have to make clocks. And the clocks must be very, very simple. What is important in the clocks? That it ticks. Tick-tack, tick-tack. So this is two events, tick and tack. This is just two marks that between tick and tack there is some measure of time occur. So in this tick-tack principle we make idealize. We make very simple device with source of light and detector of light and one mirror. And we say tick, that means I send light, and tack, I register light. And this is my simple tick-tack system, which I can measure the light, the time interval between tick and tacks. So now, if I know this distance, measured somehow exactly distance between two mirrors, then for me here, there will be relation. The time interval between tick and tack is exactly given by this. Speed of light times t divided by 2 is L. Now, I put the same device in the rocket, moving with velocity u. What I will see? That because everything moves, my now light will not make the path L, but the path will be longer, because it moves not in straight line, but make this zigzag. So the time which is spent to pass from this point to that point is this little t. Here is a capital T. Again, in this direction, light must move with the same speed as here. So it will be c times t divided by 2. And in this horizontal direction, it will move in the same time interval t half by u times t half. So then this length I can easily calculate. Again, this is the Pythagoras theorem. So this is hypotenuse, which length I know. This is one of the cathets, and I want to know this distance. I formulate it like this. And now compare this and this side. What I have is that time which measure my clock here when it's at rest, and ticking, tacking in the rocket changes. So this is the relation between capital T of the clock at rest and clock which moves with the speed u. So now observing some clock moving in the rocket. For the guy in the rocket, with respect to the clock tick-tack system, it doesn't move. So he will measure this time, T capital T. But for me, standing on the Earth and looking in the rocket passing, the time which I see the clock's measuring is this small t. And this small t is multiplied by this square root. This number is smaller than 1. So if I measured, for example, 1 year, the rocket passing, then I know that for the guy in the rockets, it's not 1 year, it's 1 day. If this number is sufficiently small, and this u is very, very close to c. So for me, standing on the Earth and the guy in the rocket, the time runs differently. Because, again, of this property of that the light, that in all direction in any system it must move with the same speed, because the equation of electromagnetism, Maxwell equation, are invariant. They are the same in all systems. And this experiment was done to check this theory. It's so-called Heffeli-Keating experiment done in October 1971. Two astronomers, what they did, they bought 4 clocks, very precise cesium beam atomic clocks, extremely expensive, and put on the board of standard commercial airplanes. And sent 1 clocks in around westward to around the Earth and eastward, so it's along or in other direction with respect to Earth rotation. And of course 2 clocks remains here at the base and Naval Observatory Station. And then they flew several times, twice around the world, and compared the clocks. And it turns out that the time showed by the clocks where they're flying in different direction and stay put on the Earth is different. And here is a typical difference. If you go one direction, it will be delayed. Another one will be advanced. And these numbers, this one, it compared rather nicely with the calculations, the prediction by the theory. So all the price of this experiment was $760 of that time, 71. They are more valuable, of course, but still, this is the cheapest experiment on general relativity. So these things which happens here, although it's idealization, of course, we are not constructed, or devices are not just tic-tac system, but nevertheless, this relation between time also applicable to the macroscopic objects. Okay, now, so what we can from Newton world description is not valid anymore. We have to combine in our description also time. So the main statement of Einstein, it was done, Einstein-Minkowski Poincaré, that we are living not in 3-dimensional world plus 1 global time, but we're living in 4-dimensional world, where each event must be characterized not by 3 numbers, but also by another, which represents coordinate, but also by the additional number time. So whatever happens, so all our life can be described by the sequence of different events with different labels. xyz capital T and xyz small t. So this event, sending photon, absorbing photons, or the electron goes from one point to another, and so on, on the macroscopic level, is described by 4 numbers. Okay, but how now, the question is, what is invariant distance between 2 points in this 4-dimensional world? It turns out that it's almost Pythagorean. So you see in coordinate there is a plus, 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 but the time comes with minus. So if you make such a transformation, not Galilean one, but so-called Lorentz transformation, which kept this structure invariant with respect to any motion, with any velocity, then you must, and also the Maxwell equation must be invariant, then you must put here minus. So actually, if we forget, for example, about z component, and say this is x direction, this is y direction, there is no z, and this is t, then we are living on this type of hyperboloid. This is my point where I'm currently, or the one cell, one electron in my brain is in this point, then for this electron the future will be here, and here will be the past. Okay, what is important now for us is these signs, plus, 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 minus. The mathematician likes to separate these numbers somehow and invent these so-called matrices, or they call it tensors. You see here is again the same 1, 1, 1 and minus 1 and these different sums. And this structure, which directly represented here in the signs, for some simple case, is called metric tensor. So this metric tensor controls geometry on our basic space, or it's not space, or the time space as we call it now, locally in this particular point. And this object, G mu, or the G with the 2 indices, which just numbers the elements here, it turns out can be changed, and it's changed by the gravity. And Einstein and also David Hilbert, they derived equation for this letter G mu. So here is in Leiden in the university where Lorentz worked, is this panel where you can see this famous equation for the general gravity. So G mu you can see here, this is some constant factor, and this is R, this is derivative of this function G mu, how it changes in different space-time points. So this is differential equation. And what is the source of differential equation? Is this term, which is nothing else basically, is the energy. Energy and momentum density. So energy leads to the changes in the way how my generalized Pythagorean theorem in space-time time-space changes. So the gravity changes this metric, so-called metric of our universe, metric tensor. And through this metric tensor, it changes how the body moves around the gravitational objects. So what our gravitations are is exactly these little ripples on this metric, the perturbation of the metric. The question sounds?
Questions, yes.
Time dilation, okay, it was from Tobias Mihalchik. I think this is the question to that one. Here is nanoseconds. Okay, this time dilation, if to this one is nanoseconds. 10 to minus 9 seconds. It's really small. Yes, it's Minkowski metric. Although it's, okay, it's a little bit depends, of course, that we are in gravitational force field of the Earth. But if you made, okay, if you move straightly on one height, then of course you can average it out. But in general, of course, for calculation must be taken into account in what is the gravitational field of these clocks are. So this is exactly what I'm telling now. that these calculations basically are done with this kind of metric. This is called Minkowski metric. But this Minkowski metric will change in the presence of gravitational field. But on the Earth, Earth is not heavy enough to change it dramatically. So gravitational wave is excitation of this metric field. And the first ideas to measure it, going back to the Weber's experiment, 1960, where you take this aluminum cylinder, 2 meters long and 1 meter in diameter, and surrounded this from piezo detectors, which are sensible to changes in little changes in the position of the points of the surfaces. And of course it was specified for one particular frequency because it's fixed size, and was estimated that maybe it's the so-called primordial gravitational wave which we created at the Big Bang. That we still can observe them, and they will be, this detector must be sensitive to this wave. But of course, it turns out that it's not sensitive enough. Okay, it's 1960, the people start to think about measurement of gravitational wave. In 1960, the first optical laser was built, and immediately Gertenstein and Pustovoit suggested what can use the laser because it's the waves with well-tuned wavelengths can be used to build interferometer on this hand, like Michelson Morley built this interferometer to see if the lengths of these two arms of the spectrometer changes. If you send the light in these directions, light from here, and split it into direction in this arm and that arm, if the length of one arm changes with respect to the length of another arm, you can see interference pattern when these two beams will come back. If the interference, two waves coming in the same phase, you see the maxima in the same place as the minima, then it is constructive interference. The signal will be bigger than the signals of these two waves. If you shift now the little bit dephased, then the height will change, and you can even reach if you're completely out of phase. So for each maxima in one wave there is a minimum in another wave, you will see nothing. So it appears so-called interference pattern which can be detected. So suggestion 1962, the build-up comes 10 years ago. This is LIGO, Laser Interferometer Gravitational Wave Observatory. Consists of 2 points, so again 2 arms here, but of course it's not just 4 kilometers because the beam goes here many times, so it's 100 kilometers actually arm length. And here then there is the test mass, and there is on the test mass there are absolutely nice mirrors. So test mass is 40 kilograms with a mirror attached to this, and here there's a special pendulum system which weight is much higher, the 360 kilograms, heading to prevent the transition of even microscopic vibrations from the ceiling, from the earth to this mirror. And the mirror is hanging on the several tens of fibers which are 0.4 millimeter thin. So it's really spectacular, fantastic engineering construction, physical one. And there are 2 detectors. Of this side built one in Hanford, another at Livingstone, because you need coincidence. Because to get to distinguish between the smallest vibration of the Earth, so if some gravitational wave will come, then the same signal, because of changes in the length of the arms of this interference signal, will be observed here, and then with some delays in another station. And the people start to analyze the data. So it's continuous analyzing data and comparing this. And the first event was measured September 14, 2015. So this is data in Livingstone data and Hanford data. and here the comparison with the prediction of typical merging of two huge astrophysical objects. Two black holes with a heavy, massive, it was tenths of the sun masses. So was some period when a spiral, they start to touch each other, and then there is merging together, and then there is final vibration, and you see that the observation, especially here when signal becomes strong, agrees exactly with the observation. Of course, they had particular templates. They knew how this signal must look like. And what we did in continuous signal, we are comparing this type of the observation with the templates. And this template, or the agreement with the templates, must occur simultaneously at Livingston part of the detector and Hanford part of the detector. Simultaneously, of course, with time delay needed for the gravitational wave with the speed of light passing from one town to another town across the United States. Okay, so what we have now, that was the first event, then next year was another event. What we have now. So here on top, all these, the pairs which are linked together, this like the grape clusters hanging together, this is observed events of the black hole mergers. So what's shown here, this is the masses, in solar masses. This is huge object. So the two objects here, for example, with these masses, they merged and produce object with this mass. They're not always equal to the sun, because some masses are least distributed anyway. So important, what was found is not only in blue, is that we don't see objects, we just get the gravitational wave signals. Here, this one, what is in violet color, if you can see this is distribution of the electromagnetic black holes which can be seen. So we know that electromagnetic sources tell us that there is some this gravitational object. We see that also here, although there we don't see the explicit merger of these two black holes which we can see, but there are mergers in this mass interval. But what was more spectacular is that what observed several events, like this one, this in orange, where the small mass object merged together. The small mass means the masses about 1.5 and 2 solar masses. And these stellar objects, we don't see the signal in electromagnetism on the other spectrum, or the optical. These are called neutron stars. So it's light compact object. Neutron star is sun, or the dead sun, when at the end of its evolution can form either black hole or the neutron star, when the whole it's compressed and all matter is transformed into neutrons, neutral particles. So its mass is about 2 times solar mass of the sun, but is compressed to the radius of about 10 kilometers. So it's small but very heavy object. And what was observed, that indeed one can detect merger of these objects. So this is the big discovery, because here in yellow shown the neutron stars which are seen through different ways for other electromagnetic radiations, and also optically as remnants of supernova explosions, also as the pulsars, some beeping stars. So these are indeed events which happens currently in the universe, and observation of these two events changed our understanding of how frequent neutron stars can merge. And the merger of neutron stars nowadays is considered as main sources of all heavy elements in the universe. So before, for example, all gold which existed on the Earth and the whole universe was, people thought, is mainly produced in supernova explosions. It turns out that large contribution of other elements also, heavier elements, the considerable amount of these elements can be produced not in supernova explosion but in mergers, or distributed in the produced and distributed in the universe. So now we enter a new era in astrophysics and astronomy, so-called multi-messenger astronomy, because now we not only see through telescope or through radio telescope or some gamma ray telescope or X-ray telescopes, like electromagnetic waves in various parts of spectra. There are several neutrino telescopes, big neutrino detectors built in the world. Kande, Baksan laboratory, Mont Blanc detector. Nowadays we can see sky through the gravitational waves. Okay, that's all. Thank you very much for your attention. So this is a nice picture from the film Interstellar for everyone who want to indeed see science fiction based on the science, not on the fiction. I could advise to watch this movie. And actually for this movie, so this picture was indeed calculated by Kip Thorne, how one would see neutron, the black hole. Because people knew that there must be some disk, accretion disk around black hole. And it was an old picture that it was just the disk about empty space. But Kip Thorne calculated that the way how we will see it, because of the change of the passes of the light around the black holes, we will see also backside of this disk. So this picture first appeared in the movie and then appeared in scientific picture. Moreover, all the formulas which you can see in Interstellar, they are correct, written by Nobel Prize winner Kip Thorne. Again, thank you very much for your attentions, and now I will get some, see if you have other questions. Okay.
There is a question. Can you see?
Last one?
There's
some soapy title.
Shall I read it for you?
The last one.
Yes.
This okay, so this is okay. This is not electromagnetic black holes. This is what probably sorry, I go back here. So there are objects which we can see in, because there is some, yes, these EM black holes, it doesn't mean that they're electromagnetic. That means we have objects, there is some stuff around them. Like, for example, in the center of our galaxy, there is the hot bulb, because the matter collides, because of the attraction, matter is absorbed there, and it's heat up, and it radiates. So this is electromagnetic radiation we can see. And on this plot, it was dictated like EM black hole. So this is nothing special. It's just a black hole which is seen for us through the optical spectrum, through the electromagnetic waves. The same neutron stars. Neutron stars, because it's magnetized objects which are very rapidly rotates, and strongly magnetized, there is the beam of radiation going from some pole caps, some spot, not on the pole cap, some spot on the close to equator, on somewhere, and this spot rotates, and we see how this beam of electromagnetic radiation passes through the Earth's surface, and we detect it as like a peak. So this peak, we can quotation mark here, or detect on the Earth, and that's why I also mark EM, that these neutron stars we absorb through the electromagnetic radiations in the form of pulsars. So again, black holes is so-called normal black holes, although we don't know what it is, but we know they are there. So this is just to indicate that, okay, the first, of course, data were here in the high mass diapason, because the signal is, of course, much stronger if the two very heavy object merges. Still now with increasing the sensitivity and watching longer, the people start to see the events between objects with lighter masses. And this is to see that these events which they saw, for example, these masses of the primordial two black holes are in the range of the masses which are already seen. There is nothing strange. So we can indeed attribute these two blue dots to the, say that they are similar to this violet. And here is the same logic. Why they shown here EM stars? Because this is what we know exists, we have seen here, and this is three events which were observed involving the object with the mass from the same diapason. So this is comparison important for identification that two primordial objects were either black holes or neutron stars. Okay, questions? Okay, I hope that I answered your question. So let me scroll through. Okay, so sorry for the echo in the beginning. I have not realized, although I switched off the dynamic on the computer. Okay, Minkowski Metric I tried to explain. Yes, in the first part, the experiment was basically Minkowski Metric. Okay, if not, then again, thank you very much. Here's.
There is one more question in the end.
Yes, okay. Okay, this is very nice question actually. How we would measure the radio? Okay. Okay, the surface, so there is the concept of the surface of black hole. Again, this is a question that it's not 4 pi r squared. This is not such a good concept because the radius is not well defined. The concept of the distance here is not well defined again. So that's why when people speak about black holes, they operate with the mass and the entropy. And the mass is determined, so-called the temperature distribution of the so-called radiation, and entropy is related to what is called the surface. So the concept of this 4 pi r squared and the size of the black hole is the kind of question which should not be asked. Because again, as you properly said, that the measurement of the distance between the center and to the border or to the horizon is what you cannot make, actually. So it's ill-defined question. But
okay, I came to help you because the boy is only 13 years old who asked. Ten chlapec má len 13 rokov, takže on sa pýta, že či tá čierna diera je guľa. Či je to guľa a môžeme vlastne odmerať jej povrch.
No, the question again is very nice. It's a question which cannot be asked because concept of the distance does not exist. So
na tej čiernej diere nemôžeme merať dĺžku? Tam sa nedá?
Inside.
No, keď sme v čiernej diere, nemôžeme odmerať dĺžku. Nie. No. Lebo čo? Lebo nemá rozmer? Nedá sa? dá sa odmerať len hmotnosť.
Hmotnosť a entropy. This is somehow related to the surface.
A teplota, hej, ale sa pretede. Čiže tam nemôžeme merať, vôbec nemôžeme merať dĺžku, že nevieme, aká je veľká.
Áno.
Ale keď je niekde vo vesmíre, keď si myslíme, že niekde je, tak tam musí zaberať nejaký priestor, nie?
Áno, to neznačí, že ona tam... Because we never can reach it. So it's not the point, if you come to the black hole, for you it will be like infinite fall on the... So you will find fall on the black hole, but for observer, which is outside, everything will be frozen. You will never reach it. So you don't know where it is.
Čiže, a keď budem ja v tej čiernej diere, tak ja budem vedieť, že som v tej čiernej diere? Či to už je...
This is speculation. This I cannot answer exactly, but actually this is shown in the film Interstellar. This is discussed.
Čiže len vlastne, ale treba, keby som sa približovala k čiernej diere a vošla do nej, tak ľudia ma budú vidieť, kým sa budem približovať a potom zmiznem.
Nie, to
neviem.
So they will not see how you approach. You will never approach it.
Ja nikdy ju nedosiahnem.
Everything will be frozen.
Keď už budem v tej diere. Čiže to pre tých, čo sa budú dívať na mňa. No, to je ťažké.
No. But the question I like because it's exactly points that there are some questions which you cannot answer because the standard physical quantity like a distance is based how you measure it. Because if you cannot send the runner back and forth, which tells me how far it is away, because nothing came back, so this question disappears.
Čiže ja keby som išla k čiernej diere, nikdy sa k tebe nevrátim, tak vlastne nevieš, ako ďaleko som zašla. Ale vidím, že tam pribudli nejaké ďalšie poznámky alebo otázky. Rozumiem. No, tak ten chlapec to porozumel.
Okay.
Čiže tak pozdravujeme Tobiasa. Porozumel tomu lepšie ako ja, takže sa teším. Super.
Dobre, dovidenia.
Takže učíme sa zo všetkých